to take a look now at vector value functions. And a vector value function is one that assigns a vector to each point in either the plane or in three-dimensional space. So what we'll do then is we'll write this as f of x, y, z, for example, in three-dimensional space, equals p of x, y, and z I plus q of x, y, and z j plus r of x, y, and z k. Right? The idea here then is simply this: to each point in three-dimensional space here, a vector is assigned. Right? Some of them may be larger, some smaller. Right? Some zero. Okay. Sometimes we'll write the vector symbol above the letter, indicating that you're dealing with a vector value function. An example of a vector value function which you're already familiar with is that of the gradient. The gradient of a function f of x, y, and z is the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk, where each of these partials is computed at the point x, y, z. So what the gradient does is it assigns to each point x, y, z in space a vector, namely this specific vector right here. A function of x and y, right? A vector value function. We'll also use p of x and y I plus q of x and y j to denote such a function. Frequently the letters m and n are also used here for vector value functions of two variables. Let's take a look at some examples. Right? If we let say f of x and y be equals to I, right? This is a vector value function in the plane, and to each point it assigns the same vector, namely I. So you can imagine this then as having a unit vector assigned at each point going off to the right here. Right? Such a vector value function might represent something like a wind. Right? In comparison, f of x, y, and z equals to I looks like this. At each point here, there's a vector in the x direction. There's x, y, and z heading toward the x direction here. Again, you can think of either of these things as being a sort of a wind. F of x and y equals to xi plus yj in the plane. The vector at any point here is the magnitude, as for its magnitude, the vector that's the position vector at that point, and its direction is in the same direction. So what this vector value function does then is at each point it assigns a vector that goes away from the origin and has as its magnitude the magnitude of the position vector where the given vector starts. So like so. Right? You could think of this as a repulsion. Right? That's to say, at each point, if you thought of these as forces, there's a repulsion going away from the origin. Let's look at f of x, y, and z, or let's look at f of x and y equals to yi minus xj. At each point in the plane here, there's a vector at this point, and its magnitude is the same as the position vector going to the point. Right? except its direction is perpendicular. The position vector at this point, xy, if you dot it with yi minus xj, you get 0. And so it's a perpendicular vector. It happens to take on the direction like so, counterclockwise to the position vector. And so that at each point of the plane here then, there's a vector counterclockwise to the position vector at the point and perpendicular to it. You can think of this as some sort of a twisting, perhaps, huh? Or a swirling. So, again, the vector value function, it's put that these can have many physical applications, assigns to each point in either three-dimensional space or in the plane a vector at that point. We're going to need several things that operate, so to speak, on vector value functions in the same way that the gradient operates on ordinary functions. The gradient of a function f of x, y, and z is the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk. And what it does is it takes a function here and it associates with it a vector value function. All right? So the idea behind an operation is that it is some sort of a map that takes something of one particular type and changes it into something of another type, or takes it to something of another type. The gradient then is an operation on functions of a point. On real valued functions of a point. RV here for real valued. We're going to want a couple of operations here that operate on vector valued functions. And the first of these is going to be called the divergence, written divergence of f, or delta dot f. Right? And what this is as follows. If f of x, y, and z is equals to p of x, y, and zi plus q of x, y, and z j plus r of x, y, and z k, then the divergence of f is going to be a real valued function. It's going to be the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. So what the divergence operator does is it takes a vector valued function and associates it with it a real valued function at each point. Namely, at each point, the real valued function is the partial with respect of p with respect to x plus q with respect to y plus that of r with respect to z. If we're just dealing with f of x and y, a vector valued function here, equal to p of x and y I plus q of x and yj, then the divergence of f is equals to the partial of p with respect to x I plus the partial of q with respect to yj. So in this case here, this is the divergence. Otherwise, it's like so. The divergence acts like a derivative. In fact, sometimes one writes this. If one uses this gradient symbol here, or triangle, to represent the partial with respect to x plus I plus the partial with respect to yj plus the partial with respect to zk. Now here there's something missing here. All right, and this is just a symbol, so to speak. However, you can treat it like as if it manipulates, in particular, a function f by giving you the gradient of f, which is going to be what you get if you put f in here in each of these three places. That's to say, the gradient of f is the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk. Right? So you can think of this as operating in this fashion here. You put f in here in the blank spots. Likewise, gradient dot, a vector valued function, is what you get if you put p, q, and r in here and remove the I, j, and k, just like as if you were performing a dot product. So it's the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Now, the gradient operates very much like a derivative. In fact, it's perhaps the natural generalization of the derivative, but the divergence also acts like a derivative in the following sense, for example. The divergence of a constant times a function is a constant times the divergence of the function. Right? Also, the divergence of the sum of two functions, two vector value functions, is the first, the divergence of the first, plus the divergence of the second. These two properties are what's called linearity, and this indicates that the divergence is linear. A third property is more like that of derivatives, though. That's to say, if we take the divergence in this notation of a real valued function times a vector valued function, right? This is going to be the first times the divergence of the second plus the second the vector valued function. I'm sorry, the first times the gradient times the divergence of the second plus the gradient of the first times the second. Right? So this is similar to the fact that the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. Here we have the divergence of f times g is equals to f times the divergence of g plus the gradient of f times g. And of course, g is replaced here with capital F. Let's see that that's the case. If we've got f times capital F, we want to compute the divergence of it. The divergence f times capital F is little f times p I plus little f times q j plus little f times r k. Right? So we wish to compute the divergence of this, and this says that what we want to do is we want to take the partial of this first term here with respect to x. Well, since the partial derivative acts like a derivative, this is going to be the first times the partial of p with respect to x plus the second p times the partial of f with respect to x. Right? This plus, now, the partial of f with respect to y times q plus f times the partial of q with respect to y plus the partial of f with respect to z times r plus the partial of r with respect to z times f. Well, if we add these up here, this first sum here is f times the divergence of capital F. And the second sum here is the gradient of f right, divided interpretation of this is that this is the dot product right here. This little f times divergence of capital F, this is scalar multiplication, right? And so you get this formula here, which is sort of a derivative type formula, and indicates that the divergence is a sort of type of derivative. Now, what does the divergence do? The gradient points in the direction of maximum increase of the function little f and tells you how much that increase is. What the divergence does, roughly speaking here at least, is at each point here, you look at the partial in the I direction and the partial in the J direction and the partial in the K direction. That tells you the extent to which capital F is increasing in the I direction, and then you add on the increase in the J direction, and you add on the increase in the K direction. If you think of this as some sort of a velocity vector for fluids, that's to say at each point here you have a fluid and it's flowing in a particular direction, then what this indicates, if there's a positive net effect here to these three partial derivatives, it indicates that there's a positive quantity of being created, so to speak, or pouring into that point. It's actually leaving the point. There's a velocity to this fluid leaving the point. If you end up with something that's negative, you've got something, there's, for example, when you add the increase in this direction to the increase in the other three directions, you end up with something negative, right? You similarly have something leaving the point. All right, and if there's a zero, it means that the net flow away from this point, so to speak, using the word flow poetically here, right, is zero. The amount that's coming in the x direction adds up, and the y direction and the z direction adds up to zero, right? So this is then the divergence, which is the first operator that we're going to look at on vector value functions of a point. Now we won't be using this for a little bit. We're going to be looking at another operator which we will use later also. We want now to take a look at an operation on vector value functions. Let's say f of x, y, z equals to p of x, y, z plus I plus q of x, y, z j plus r of x, y, z k. We want to look at an operation which is called curl. And what this operation does is it takes a vector valued function to another vector valued function. And specifically, what it does is as follows. This is written curl f, or sometimes delta cross f, where if you think of delta as the partial with respect to x I plus the partial with respect to y j plus the partial with respect to z k. If we cross this with f, formally here, if we think of f now as pi plus qj plus rk, we're going to get curl f. That's to say, curl f is, it's a vector valued function. It has an I component, a j component, and a k component. All right? The I component is what you get if you take j, k here, partial of r with respect to y, minus kj, right? Minus the partial of q with respect to z. That's the I component. the J component is what you get if you take Ki partial of P with respect to Z minus the partial of R with respect to Y. And the K component is what you get if you take Ij partial of Q with respect to X minus the partial of P with respect to Y. Right? Now, it's not a bad idea to memorize how to do this. That's to say, this has an I, J, and a K component. And for the I component, what you do is you use the other two parts here, namely R and Q, and you sort of go backwards here. It's the partial of R with respect to Y minus the partial of Q with respect to Z. For the J component, right, think of this as going backwards. Now you use P and R, and you go backwards around this way, so to speak. Take the partial of P with respect to Z minus the partial of R with respect to X. This ought to be an X. Right? When conjectured, it should be an X. For the K component, you use the other two here, and you go backwards, so to speak. You take the partial of Q with respect to X minus the partial of P with respect to Y. And this then gives you the curl. Right. This curl tells you the amount of swirling, just very poetically, very right? The amount of swirling that occurs at the points, and it does this using the right-hand rule. That's to say, if the original vector field has a lot of swirling going around this point in the counterclockwise fashion, then the curl is going to be in this direction here, right? And it's going to point in the direction in which the swirling takes place the most, and the magnitude of it is going to be, so to speak, the amount of swirling that occurs there. Now, the curl also behaves a lot like a differentiation. That's to say, the curl is like a derivative. So that what you have here is the following. The curl of a constant times a vector value function is constant times the curl of the vector value function. The curl of f plus g, two vector value functions, you can add them at each point, is going to be the curl of f plus the curl of g. These two facts are easy to check here just by doing the computations. The curl, if we write it in this notation here, of a scalar function times a vector value function here is going to behave more like a derivative. That's to say, if we did this as the first times the curl of the second plus delta of the first, the gradient of the first, times the second, all right? We're going to get a correct formula out of this if we interpret the multiplication properly. That's to say, the curl of f times capital F is going to be f times the curl of capital F. So this is f times the curl of capital F, the first times the derivative of the second, plus capital F times delta of little f. Right? So delta of little f cross capital F. Now this takes some checking here to see if this is the case. Right? The curl has a couple of other interesting properties in relationships to the gradient and the divergence. A curl has no divergence. Divergence of curl of f is 0. takes this to a scalar at each point, and when you do this, you find that the curl of the divergence is 0. What is the divergence of curl f? Well, if this is curl f here, for the divergence, we should take the partial with respect to x first of this part here. So that's to say we take the partial of r with respect to y, and then with respect to x, minus the partial of q with respect to z, and then we take the partial of this with respect to x. Now we take the partial of this with respect to y, so that's the partial of p with respect to z, and then with respect to y, minus the partial of r with respect to x, and then with respect to y, and then finally here we take the partial of this with respect to z. That's partial of q with respect to x with respect to z, minus the partial of p with respect to y, and then with respect to z. And what we get here is this. This is the negative of this, and so that adds up to 0. By the equality of mixed partials here, it doesn't matter whether you do this xz or zx, this part adds up to 0, and this part adds up to 0. And so we see that the curl followed by the divergence gives you the number 0. That's to say the function which is 0 at every point in space. Right? A gradient, right, has no curl. That's to say if we take a gradient and we take the curl of the gradient of a function f, we get the 0 vector at every point in space. Well, gradient f is partial f with respect to xi plus the partial f with respect to yj plus the partial of f with respect to zk. What happens if we want to compute the curl of this? Well, it's got an I component, and that's given by taking the partial of this with respect to y, so f zy minus the partial of this with respect to z, f y z. That's the I component, and that's clearly 0 because these partials are equal. Right? Likewise, the j component is 0, and likewise the k component is 0. So you can compute very easily here that the curl of a gradient is the 0 vector. Okay, so this is gradient f, and here we've computed curl of gradient f. All right, we're going to be needing the curl later, and so this is a good time to familiarize yourself with being able to compute the curl of a vector-valued function. Again, it indicates the amount of swirling that goes around the point, and it's a vector in the direction using the right-hand rule of maximum swirl. If we've got f equals to pi plus qj, then the curl of f has only a k component, and that's given by the partial of q with respect to x minus the partial of p with respect to y. That's k times k. That's for functions defined on the plane of x and y. The curl has only a k component, and it's given by this. You can see here from this that that's the case. Right? Here, for example, if we've got f of x and y, there's no r term here, and the partial of q with respect to z is 0. Here, there's no r term in the partial of p with respect to z is 0, so you're only left with this component, the k component here of the curl, if there's no r term up here. We have another topic to look at here, and eventually these will all be coordinated to some extent. This is called line integrals, and perhaps this should be called path integrals, and sometimes it is, or curve integrals, because the idea is this. You're given a curve C, given by r of t, which is x of t, y of t, z of t. x, y, z. And we're going to use s for distance. And what we want to do is this. We want to define what's meant by the integral along the path c of f of x, y, z with respect to distance. And the idea is basically this. You have this curve C here, right? And it's got a parameterization for t in interval AB. Right? So if we take t and AB, right, this might be R of A, and this R of B. What we wish then to do is to partition up AB here, and that's going to result in a partition here of the curve, and we wanted to take a look at this integral, which is going to be the limit as the partition goes to 0, right, of at each point here, we wish to select the point ti in the interval, and that's going to correspond to a point here, like so. We want to take the sum of f of the value r at ti. Right? We want to multiply that by the length of the curve here, which is going to be delta si. In short. So this is going to be the definition here then of the path integral. We take this sum I equals 1 through n, and the limit as the norm of the partition goes to 0. And this is going to be the path integral. All right. It turns out here that the particular r that's used to describe this curve does not matter. That's to say, if you do this with respect to a different parameterization, you'll get exactly the same value for the integral as with this one. If we were to, instead of, let's say, map CD, u in CD, and t was a function of u, then if we instead looked at r of u, a different parameterization, we're going to get the same integral as this. To evaluate this integral, of course, you don't want to just use the symbol or this right here. What you want to note is the following. That delta si corresponds to the ds up here, and ds is equals to the square root x prime of t squared plus y prime of t squared plus z prime of t squared dt. This is the standard substitution that you make for ds. And so that this integral is going to be equals to the integral from a to b f of r of t square root x prime of t squared plus y prime of t squared plus z prime of t squared dt. And here note that if you're given a curve by a given shape here and a function, any parameterization of that curve will result in the same integral here. You can see that by making the substitution in here. T is t of u, all right? And x prime, for example, is x prime with respect to u is going to be derivative of x with respect to t times the derivative of t with respect to u. You're going to get the integral, right, from c to d, f of r of t of u square root dx du here is dx dt squared times du dt squared. This du dt dt squared is going to occur in each one of these here. The x dt squared times the u dt squared is going to occur in each one of these here. And so consequently we can bring it out from the square, under the square root. I want to do this with respect to u here, so that the partial of x with respect to u is going to be partial x with respect to u times partial of partial x with respect to t, partial of t with respect to u. That's going to be squared. It can come out from the square root here, and we get plus the derivative of y with respect to t squared plus the derivative of z with respect to t squared, and then we're going to have the derivative of u with respect to t dt. Right? Now these should all be u's. Okay, if we write this in this fashion right here, we found that we've changed this over to an integral from c to d. With respect to u, the dt's here act like as if they'll cancel, and you get the resulting integral. And it's the same integral exactly as this right here. This is f of r of u. Partial x with respect to u, partial of y with respect to u, partial of z with respect to u squared with respect to u. So this is a different parameterization, and it results in the same integral as before. Let's take a look at an example of how to do this. Let's suppose that we've got f of x, y, and z, and it's equals to, let's say, x squared y cubed z to the fourth. And let's suppose that r of t is equals to ti plus t squared j plus t cubed k for t in the interval 0, 1. Right? Then r prime of t is going to be 1. That's the I component. We want to take it and square it. The j component is going to be 2 to t, so we want to take it and square it and add that on. Z prime of t is going to be 3 to t squared. We want to take it and square it and add that on. Take the square root. This dt corresponds to the ds. Right? And now we want f of x of t, y of t, z of t. So that's to say, for x we put in t here, so we're going to get t squared times y is t squared, so we're going to cube that, so that's going to be t squared cubed. Z is t cubed, so we want to take that to the fourth power, so we're going to get t cubed to the fourth power. We want to integrate this from 0 to 1, because that's where t describes the particular curve. And so then this right here is your ordinary integral, your ordinary Riemann integral, and it is the way to evaluate the line integral of this function along this curve right here, described by this r of t. Right? Namely, you compute x prime of t, y prime of t, z prime of t. You square each one of them and add them together. And then you take f at x of t, y of t, z of t, and put it up front here and integrate from a to b if the parameterization is from a to b. So here's how to compute one of these integrals of f of x, y, and z with respect to length. We now have one type of curve integral or line integral of the function f with respect to s. Right? respect to s, we need to know c is given by some r of t, which is x of t, y of t, z of t, for t in, let's say, an interval ab. What we get here also is this, for this particular integral, if we integrate along the curve in the opposite direction, right, what we're going to get is the negative. If we integrate along the curve in the opposite direction, what we're going to get with this integral is the same quantity. All right, that's to say, every parameterization in the will give you the same quantity, because what you're doing is you're taking the value of f and you're adding up length with respect to it. That's not going to be the case here for the integral that we're going to define with respect to x, or with respect to y, or with respect to z. That's to say, the integral along a curve of f with respect to x is going to give you the negative of the integral of along. Well, if you integrate backwards, you're going to get the negative of what you get if you integrate forwards. The integral along c of f of x, y, and z with respect to x, is going to be defined by the integral from a to b, f of r of t here, times x prime of t dt. Right? That's to say, you're looking at the value of f and multiplying by delta x. We could also define this by means of a Riemann sum and see that this is the resulting integral. Right? Now, what happens here when if you define this as a sum, if you define this as the summation f of ui, vj, zk, delta xi, and the limit as the norm of the partition goes to 0, then what you're doing essentially is considering this curve here, considering the function as if it were a value along the curve and partitioning here, but adding the change in x at each point. All right? Similarly, you can do this. You can take f of x, y, and z, dx, dy, and if we change this to delta yi, it will result in the integral from a to b of f of r of t, y prime of t dt. And likewise, the integral around c of f of x, y, and z with respect to z is going to be the integral from a to b, f of r of t, z prime of t dt. Right? And we're going to combine these for that matter. That's to say, we'll talk about the integral along c of p dx plus q dy plus r dz. And this will, by this we will mean the integral of p with respect to x around c plus the integral of q with respect to y around c plus the integral of r with respect to z around c. Now right now these are just formal type things in the sense that if you see an integral like this, you find a parameterization of the curve c and you perform the respective integrals like so, one of these three here. Similarly with this right here, you wanted to do this as an ordinary integral. Let's take a look at an example. Let's let p of x and y and z be equals to x squared y. Let's let q be y plus z. Right? And let's let r be x times y. And let's let our curve c be given by r of t equals to ti plus t squared j plus t cubed k with t in 0, 1. this curve C of P dx plus Q dy plus R dz. Right? Well, what we need to do is we take P of x, y, and z, and we replace the x and the y and the z respectively with the x, y, and z parts of R of t. That's to say, this integral is going to be an integral from 0 to 1, and what we do is we take the x component here and square it, so t squared, the y component, so that's times t squared, right? And now this is with respect to x. So to integrate with respect to x, we take x prime of t, here's x of t right here, so x prime of t is 1, and this is d t. We can combine this all together here because there's going to be a dt involved in every one of these integrals. We now take q with respect to y. All right, well here's the function q. It's y plus z. So we take t squared plus t cubed. Okay. Now this is with respect to y. So we take dy dt. Y is t squared, so dy dt is going to be 2t dt. Finally, we take x times y. X is t. Y is t squared. And this is with respect to z, so we take z prime of t, that's to say z is t cubed, so we're going to have 3t squared dt. So that the entire integral then is an ordinary integral in this sense right here. It's the integral from 0 to 1 of the function in parentheses here, which is just simply a function of t. Right? So here's how then to evaluate an integral that looks like this along a curve C. Any parameterization of C will result in the same integral. A different parameterization, if the curve is the same, will give you the same integral. However, for this particular integral here, going backwards along the curve will give you the negative of what you'd get by going forwards along the curve, as compared to the integral with respect to length, where the integral is the same independently of which direction C is traversed. We want to take a look now at the use of the line integral, and one such use is that in computing the work done when the particle is moved through a force field, the work done by the force field. So the work done by F, all right, which is equal to Pi plus Qj plus Rk in or while a particle is moved. Along a curve C, where C is going to be given by some R of t in some interval AB. Here's a picture. You've got a force field here, which assigns to say every point in three-dimensional space a vector. We've got an R of t here, which is defined on the interval AB, say. So that this perhaps is R of A, and this is R of B. And now, if we think of this particle, the fact that this particle is moved through here, we want to know how much work is done by F on the particle. Right? What we can do is we can partition this interval up here like so, and that will result in a partition up here of the curve. And now what we wish to do is we wish to move the particle from here to here, and assuming that the force field is continuous, we can imagine that at some point corresponding to a point Ti in here, there's a force. And that force is approximately the same throughout that interval. So what we want to do is we want to look what the component of the force is in the direction of the motion, and that's going to be given by F dotted with T, where T magnitude of v of t. Well, magnitude of v of t like this, or little v of t. We want to take f dotted with t, and that's going to give you the component of the force in the direction of the motion here. And then we would want to multiply that by the small distance traversed, ds, and integrate this over the curve c. Right? Now here, if the motion goes this direction here and you get a positive value, then going the opposite direction will give you a negative value, because the tangent will be the negative of the tangent in the positive direction here. All right? What this is going to be is, it's going to be the integral over c. We could write this as sums here also, and we would get this resulting integral. It's going to be the integral over c of f dotted with magnitude v over magnitude v. And now ds is magnitude v dt. Right? That's to say, ds is the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt, and this is nothing more than the magnitude of v. So these magnitudes v cancel here. And so what we get then is that this is equal to the integral over c of f dotted with r prime of t. This is f of r of t if you want. Dotted with r prime of t dt. And now if c is parameterized from a to b, from t going from a to b, then this is this integral right here. The integral from a to b of f of r of t, right? Dotted with r prime of t, that's f dotted with b dt. Sometimes this is written as the integral over c of f dotted with dr. This is a very shorthand form here, which allows you to remember how to evaluate a particular integral, giving you the work along a particular curve. Let's take a look at an example. Let's suppose that f of x, y, and z is equals to zi plus xzj plus xyk, right? And let's let r of t be equals to ti plus t squared j plus t cubed k, with t in the interval 0, 1. This is an r that we've used several times. It starts at the origin here, and it ends up at the point 1, 1, 1. All right? So here's r of t. R prime of t, of course, then is going to be equals to I plus 2tj plus 3t squared k. So what do we want to do here? We want to compute f of r of t. That's to say, when we find z here, we want to put t cubed. X, we want to put t. When we find y, we want to put t squared. So this is going to be t cubed I. zi, t cubed I, plus x times z, that's t times t cubed j, plus x times y, that's t times t squared k. Right? And now what we wish to do is we wish to dot that with r prime of t. That's to say, I plus 2tj plus 3t squared k, and integrate that with respect to t from 0 to 1. This is going to be the integral of f dr around the curve c. Okay? Now we do this dot product here, and we see that we're going to have an ordinary integral. Let's say this is going to be the integral from 0 to 1. We have t cubed times 1, so we get t cubed. Here we've got t to the 4th times 2t, so that's going to be 2t to the 5th. Then we've got t cubed times 3t squared, so that's going to be 3t to the 5th. We're going to integrate 3t to the 5th, and we're going to integrate that with respect to t. So what we've got got then here is an ordinary integral, and the antiderivative is going to be t to the 4th over 4. Here we've got 5t to the 5th, so that's going to be plus 5t to the 6th over 6. Evaluating from 0 to 1 is going to give us a quarter plus 5/6. So to evaluate an integral of f dot dr or f dot tds, right? This notation here, or f dot dr, to evaluate these, an integral of this form right here, we want to take parametrization of the curve, look at f of r of t, dotted with r prime of t d to t, and integrate from the two endpoint values where the parameterization occurs. Right? If you've got several parameterizations making up pieces of the curve, of course the integral of the sum here in these cases is the sum of the integrals, and you'd add up the various pieces that were needed to get you along the curve from one end to the other. We're going to take a look now at another example of work. This is a traditional example of the work done against gravitational attraction, or any attraction such as magnetic attraction, which is proportionate, where the force is proportionate to the distance squared. If we have f of x, y, and z equals to k times xi plus yj plus zk divided by x squared plus y squared plus z squared to the 3/2 power. This is going to represent some sort of magnetic attraction or repulsion or gravitational attraction. Here k is generally going to be negative. We could even indicate that by putting minus k here. And by this is understood, the I component is x over this to the 3/2 power, the j is y over this to the 3/2 power, and the k component is z over this to the 3/2 power. With k negative, what this means is that at each point there's a x, y, z. There's a vector which is directed back toward the origin, as if there were a mass at the origin attracting a particular object. Right? Another way to write this f is to write that f is equals to minus k r, where r is the position vector xi plus yj plus ck over the magnitude of r cubed. Right? And we note then that if we write this way, that then the magnitude of f at any point is equals to minus k. We're going to compute the magnitude of r over r cubed, so this is going to be minus k over the magnitude of r squared. So that the force is, the magnitude of the force is, well, it's going to be, the magnitude is going to be plus, of course. It's going to be directly proportionate to the distance squared, which is the case with gravitational attraction. All right? Let's leave k here, and let's suppose that we wanted to move an object where k was given here. Usually the mass at the origin as well as the mass of the object would be involved in k. And let's suppose we wanted to move it from the point 0, 5, 0 up to the point 0, x is 0, y, let's say, is still 5, and z is 3. Right? We could then parameterize this curve with r of t equals to 0, 5, 0 plus t times 0, 1, 0. That's to say, or 0, 0, 1. Right? We wish to move in the k direction only, or if you want that this is equal to r of t given by 0, I plus t is equal to 0, you'd be at the point 0, 5, 0, when t was equal to 3, 0, 5, 3. Right? And the question then is, how much work would be involved in moving the particle under this field from here to here? Right? And to do this, we want to take a look at the integral from 0 to 3, f of r of t, dotted with r prime of t, dt. Right? F of r of t is going to be minus k. Here's r of t. So for x we put 0 in. For y we put 5. So this is going to be 5j. For z we put t plus tk divided by x squared plus y squared plus z squared square root cubed here. So this is going to be 5 squared plus t squared. We want to take the square root of that and we want to cube it. Right? Now we want to dot that with r prime of t. Here's r prime of t. So we want to dot that with 5j plus tk. And integrate from 0 to 3 with respect to t. Oh, I'm sorry, we want r prime of t. We want to dot this with r prime of t. R prime of t is 1k. 0i, 0j, 1k. So we dot this with k alone here. And we get that this is equals to the integral. This is the constant k, whereas, of course, this is the vector k here. So we bring the constant k out 0 to 3. And we just have the k component here, so this is t over square root 5 squared plus t squared with respect to t. This cubed. And now here, if we let u equal to 25 plus t squared, and du be equal consequently to 2t dt, right? This becomes the integral of u to the minus 3, right? 2t dt is du, so that this is du, t dt is going to be du over 2. And now we want to go from t equals 0, when t is equal to 0, u is 25, to t equals 3 to 34 here. And then we want to multiply by k, minus k throughout here. Huh? So by minus k. And of course, depending upon the particular weights of these two masses attracting each other. And now this is going to be an easy integral to evaluate, right? That's to say we take, this is 1/2 u to the minus 2 over minus 2, evaluated from 25 to 34, and times minus k. So we're going to get out of this k over 4 times 1 over 34 squared minus 1 over 25 squared. Okay. Now, this gravitational field has an interesting property, namely it is a gradient, right? And fields which are gradients are going to allow an easier evaluation of the particular line integral that gives you work. The field f here is the gradient of little f, where little f is given by k over square root x squared plus y squared plus z squared. One computes easily then the partial of this with respect to x is partial of f with respect to x is k times 1/2 this. Well, this is this to the minus 1/2, so it's going to be times minus 1/2 this to the minus 3/2. That's the minus 3/2 times the derivative of this, which is 2x. So the partial of f with respect to x is clearly right here, namely it's minus kx over this to the 3/2 power. Similarly for the partial of f with respect to y. Now, so if capital F is greater than little f, then what one may do is note that f of r of t, dotted with r prime of t, right? dt, this integral, this quantity right in here, f of r of t dotted with r prime of t by the chain rule, is the derivative of f of r of t. So we can simply take f of r of t, its derivative is going to be this. So if we take f of r of t and evaluate it from a to b, where the curve is given from a to b, this is going to be the integral. That's to say we can take the function whose gradient is this given one, capital F, if there is such a function, and we can evaluate the integral by simply taking the value of f at one endpoint and subtracting the value of f at another endpoint. What this indicates also is that it doesn't make any difference which direction c goes from the point A to the point B, the amount of work is the same. Because it's simply f of r of t evaluated at b minus the value at a. And this is, of course, this part of the theory of work in a gravitational field. The amount of work that's involved in getting from one point to another is independent of the path. Right? Such fields are called conservative fields, and we're going to take a look at them next. A vector-valued field F, x, y, and z, right, of x and y, is said to be conservative. And this is the definition. If the integral from a point A to a point B of f dot dr is independent of the path. That's to say, if it gives the same value independently of which path is taken. So that, for example, if f is independent of the path here, we go from point A to point B, it doesn't matter if we go in this direction here like so, or over here like this, or any other route here that gets from A to B. The integral that computes the work involved is going to be the same. Right? So this is the definition of conservative. And now a function, capital F, is going to be conservative. It's going to be if and only if the integral around any curve C, and where C is a closed curve, right? That means it starts and ends at the same point. If the integral around the closed curve C is always equal to 0. Here the idea is this: if we take a curve C and it goes around and ends up where it started out, then the integral of f around C, and the integral around the closed curve is going to be written integral over C, in this case of f dot dr, or whatever other thing is being integrated here. And sometimes we'll also add a small circle here in the counterclockwise direction to indicate that we're going around C in the counterclockwise direction. Here it doesn't matter. But this also indicates that it goes around C and goes back to where it started. All right? If we've got a conservative field, then the integral around C is going to be equal to 0 and vice versa. And the reason for this is that if this is a point A and this is a point B, then if we integrate in this direction to get to B, that's going to be the same thing that we would get if we integrated along this other direction to get to B, and consequently, if we integrate along this direction and then integrate back to A, we're going to get this plus the negative of that, or 0. So that shows that if you've got a conservative field, then if you integrate around a path back to a point, you get 0 for the total integral. Conversely, if you got 0 for the total integral, then that would mean that this plus this adds up to 0, or this is the same as this. Right? This is the same as this because this integral here and the negative of this one is this integral here is the negative of this one, huh? So that this integral is the same as that one. The integral going the other direction is the same as this integral here. All right. So, one way in which you can tell if you've got a conservative field is to determine that if the integral around each closed curve is 0, and better still is that you're going to have a conservative field if and only if f is a gradient of some little f. So if there's some little f, and f is the gradient of little f, then you're going to have a conservative field. Here's the reasoning behind this, the reason for it, roughly. Right? If f is gradient little f, and then if we go from along C and compute the work involved of f dot dr, right? This is going to be the integral from A to B of f of r of t dotted with r prime of t d to t. But what is f of r of t dotted with r prime? Well, it's the derivative of little f of r of t. The derivative of little f of r of t by the chain rule is the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times the derivative of y with respect to t plus the partial of f with respect to z times the derivative of z with respect to t, where r of t is given by x of ti, y of tj, and z plus z of tk, and little f is given by f of x, y, and z. All right? Then this gives this derivative of the composition. So that a derivative of this function is exactly this dot product. Because what's f of r of t? It's f is partial f with respect to xi plus partial f with respect to yj plus partial f with respect to zk if capital F is the gradient of little f. And now when we dot that with r prime, what do we get? We get exactly this product plus this product plus this product. And so we can evaluate this integral then, if capital F is a gradient of little f, by taking f of r of t and evaluating it from A to B. Right? This is nothing more than f of capital B minus f of capital A. That's to say, if capital B is one end of the curve and capital A is the other, then we take this at f of capital B and we subtract the value at f of capital A. And that doesn't depend on the curve. So that if capital F is the gradient of little f, then the integral along any path does not depend on the curve. To see the converse also holds, namely that if this integral right here doesn't depend on the curve, but then what you have is a gradient. What one can do is the following. One can fix a point, let's say A, B, C, right, equals to A, right, and define f of x, y, z to be equals to the integral from A to x, y, z of f dotted with r prime of t dt. Since this doesn't depend on x, y, z, then this defines a function f of x, y, z. Right? Now, it is not difficult to see that the partial of f with respect to x is the p part of f. The partial of f with respect to y is the q part, and the partial of f with respect to z is the r part of capital F. One simply computes, by the definition, f of x plus h, y, and z minus f of x, y, and z divided by h, and the limit as h approaches 0. What this means is that one integrates in the I direction from x to x plus h, or if you like, first to x, y, z, and then to x plus h, y, z. So this is going to be equal to the integral from x, y, z to x plus h, y, z of f dot r prime dt. And now, from here, this is divided by h, and the limit as h approaches 0. Right? Without going into the details, it's the fundamental theorem of calculus here that guarantees that the derivative of this in this direction is going to be the first component of f. Right? That's to say, this motion has nothing in the z direction going here, so that r prime is going to be 0 in the z directions, and we're going to get p dx. Right? And then differentiating, we're going to get that the partial of f with respect to x is p. Okay, so a rough outline here as to why, if f is a gradient, then the integral is independent of the path, and if the integral is independent of the path, then capital F is a gradient of some little f. Given a function f, vector value function, we want to just consider at this point functions of x and y, p of x and y, I plus q of x and y, j. We want to know whether or not f is the gradient of little f. And if so, we want to be able to find out what little f might be. Right? And for functions of two variables, it turns out that the exact test as to whether or not capital F is a gradient of some little f is as follows. If capital F was a gradient of little f, then this would be partial of f with respect to x, and this would be partial of f with respect to y. And so consequently, if we took the partial of this with respect to y, this would be fxy. It would be equal to the partial of f with respect to y, then with respect to x. That's to say it would be the partial of q with respect to x. Turns out that if the partial of p with respect to y is equal to the partial of q with respect to x, then capital F is a gradient. And it's not, obviously. All right? So one thing that you can do here is to check partial of p with respect to y. Is it equals to the partial of q with respect to x? If it is, then this capital F is a gradient. How can we find out what little f is? Right? We want to find the so-called anti-gradient for capital F when there is one. And the reason for this, of course, is to be able to evaluate integrals along paths. Well, if capital F was partial f with respect to xi plus partial f with respect to yj, then little f would be an antiderivative of p with respect to x. And this is written with this partial sign here with the idea that it would be an antiderivative of p with respect to x when y was held constant, right? Now, plus any constant here, surely, but what could also happen here is if we take the partial of this with respect to x, if we added on any function of y here, that could serve as a constant as far as the partial of f with respect to x was concerned. So what you do here is, first of all, you find an antiderivative of p with respect to x, and then add on a general h of y here. All right, we've now used this part of the information. P is the I component of the function capital F. Right? We want to use the rest of the information here, and to do that, what we do is we take the partial of f with respect to y. If this is the form of it right here, this is going to be the partial with respect to y of antiderivative of p with respect to x plus h prime of y. Right? This is supposed to equal q. Right? So what we do is we set this equal to q of x and y. When we do this, right, we want to solve for h prime of y, and we ought to be able to do that. That's to say there should be nothing but y's in here. This will allow us to solve for h prime of y. When we find h prime of y, we can anti-differentiate it, and that will give us h, and we will then have found f. It's perhaps easiest to do a particular example here to see how this works. Let's suppose that f of x and y was equals to y plus e to the xi plus x plus cosine y j. Now I have fixed this example up here so that capital F is gradient, and it should illustrate what you need to do to find that out. First of all, if this is p and this is q, we want to take a look at the partial of p with respect to y. It's equals to 1. And the partial of q with respect to x is also equal to 1. So that says that we're right in looking for a function little f here. Right? What we then have is the partial of f with respect to x is equal to y plus e to the x. So we find that f is equal to antiderivative of y plus e to the x with respect to x here. That's treating y as a constant. Or f is equals to x times y plus e to the x. And now for a constant of antidifferentiation, we have to add on any function of y. This tells us that f has this form. We want to know what h is. So to find out what h is, we take and compute the partial of f with respect to y. It's going to be equals to x plus h prime of y. It's supposed to be equals to x plus cosine y, namely q. So this is going to be x plus cosine y, at which point we find out that h prime of y is cosine y. Right? The equation at this point should have only y's in it. From this it follows that h of y is sine y plus any constant. And so consequently we have found f of x and y. It's equals to x times y plus e to the x plus sine y and plus any constant here. All right? So we can pick any constant here, and we can now check, of course, that the gradient of little f is capital F. What's the partial of little f with respect to x? It's y plus cosine. It's y plus e to the x. There it is. What's the partial with respect to y? It's x plus cosine y. There it is. So we now have found an f so that the gradient of f is capital F. And this, of course, will allow us to anti-differentiate and to evaluate the integral of f dot r dt here from a to b. It's independent of the path, and the value is going to be little f at b minus little f at a. Right? Where, for example, if b is equals to 1, 2, and a is equals to 3, 3, 4, what you do here is you take little f at x equals 1, y equals 2, so 1, 2, e to the 1, sine 2, and subtract the value at 3, 4, 3, 4, e to the 3, sine 4, and this will give you then the integral of the amount of work done by the force field along this path from the one point to the other. Okay, so how to find antigradients? If you've got a function of 3 variables here, you clearly would have to have a lot of partial derivatives equal here, and you can search for an antigradient in the same way as you do here, except that at each stage here you want to allow the most general function. Namely, if we had 3 variables here and we took the antiderivative with respect to x, we would have to include on here a function of y and z, proceed on and solve for those functions as they showed up. It's more complicated, but if you can always, if you've got an answer, you can always check and see whether its gradient is the original f, capital F. We want to look now at a theorem in the plane, or stated for the plane, that has several generalizations which are important theorems, but it's an important theorem itself. It's called Green's theorem, and what it says is this. If you've got a region R bounded by a closed curve C, simple closed curve C, simple means that it doesn't cross itself, then the integral around C in the counterclockwise fashion of p dx plus q dy, right? So where we've got f of x and y is pi plus qj, p and q are functions of x and y. This integral, this is your normal work integral going around this curve, is given by the double integral over the bounded part here of the partial of q with respect to x minus the partial of p with respect to y. And then this is with respect to area. All right. We want to look at this in several cases here, and the first of these is to see that this is true. What actually happens here is that this integral of p dx is this integral right here of partial p with respect to y dA, and this integral right here is this integral. All right? The first situation here that we want to look at is when the region is a simple one. That's to say it's between a and b, and it's bounded by g1 of x and g2 of x. So this is from y equals g1 of x to y equals g2 of x. All right? And let's then look at, around such a region, the integral of p dx around this region right here. We're going in the counterclockwise fashion, and if we do this, we find that we can write this as two curves, C1 and C2. These two curves here go upwards in the y direction here, and when we write them, we're going to find that dx is 0, so that this is going to be equal to the integral along C1 of p dx plus the integral around C2 of p dx. These other two integrals here along these curves with dx equal to 0 are going to be 0. Now, C1 can be given by r of t, right, equals to t g1 of x, g1 of t, with t in the interval ab. by r of t, which is going to be t, g2 of t. Right? Now we're going in the reverse direction, so we want t to be in the interval b to a. Let's say going back from b to a. So what this integral then is going to, along these two curves, is going to be the integral of p of t g1 of t dx dt dt, which is the same thing as dt. Let's say p of x, g1 of x. dx dt here, since dx dt is 1, we can write this as dx dt 1 dt. We want to integrate from a to b. Minus the integral from a to b, because we're going to go from b to a, of p of t and g2 of t dt. That's this integral right here. Let's take a look at this integral right here. If we were to take and integrate over the area, the partial of p with respect to y, we could do this by integrating from g1 of x to g2 of x, partial of p with respect to y. Integrate this with respect to y first, and then integrate from a to b with respect to x. Alright? Well, an antiderivative of this with respect to y is going to be p. And so this integral right here is going to be p at g2 of x. We want minus the integral, because of the minus sign here. Right? This one here and this one here. It's going to be the p of, it's going to be equals to p of x and g2 of x minus p of y, p of x and g2 of, and g1 of x. And then we integrate this from a to b with respect to x. Let's say we've just performed this integration in here. And now we wish to integrate this. We have a minus sign here, so we can bring that minus sign inside and get minus and plus. And this is exactly what we have here. That's to say this is the integral from a to b of p of t g1 of t dt minus the integral from a to b of p of, let us change to x, of course, here, but x g2 of x dx, that's this integral right over here. So the fact that these two are equal here shows that this integral in the Green's theorem is this integral over here. The fact that the integral of q with respect to y around c is this, right, can be shown similarly here using a region that is simple in the other sense, like so. The consequence of this is that Green's theorem is going to hold if we integrate around any region which is simple in both senses. Now, two types of regions which are simple in both senses are triangles and rectangles. And now if we wish to integrate around a more complicated region, what we can do with this is partition it up like so. Approximate each of these integrals with triangles and rectangles, like so. And now when we integrate around each of these rectangles or triangles, right, we find that the integral going in this direction is negated by the integral going around here in this direction, and so that the integral, all of these little integrals add up to the integral around the boundary, approximately and exactly in the limits. But all these little integrals are the integral over b of this quantity here with respect to area, and so they're going to add up to this integral right here. And so that this then shows that at least in outline form, that Green's theorem here is going to hold whenever you get a simple closed curve. Simple means it doesn't cross itself, and closed, and going in the counterclockwise direction, enclosing a region B. This theorem right here is going to hold. Green's theorem says that the integral around C of P dx plus Q dy is equals to the double integral over B of partial of Q with respect to x minus the partial of P with respect to y. And this is an area integral. Recall here that Green's theorem is proven by showing that this integral is this integral, and that this integral right here is this integral right here. Before we take a look at some examples, let me just note something, and that's this, that if we let P be equal to y here and Q be equal to 0 in Green's theorem, we get then that the integral around C of y dx is equals to partial P with respect to y, the negative of it is going to be 1, the partial Q with respect to x is going to be 0, so this is going to be the double integral of minus 1 with respect to a over b. This is usually written as this. The integral over b of minus 1 dA is the integral around C of minus y dx. This, of course, is the area of b, and it indicates that you can compute it by computing the integral around C of y dx, minus y dx. Right? Similarly here, if we let P be equal to 0 and Q be equal to x, we get that the integral around C of x dy, right, is equals to the double integral around b. Here we now take the partial of q with respect to x, that's 1. Partial p with respect to y is 0, dA. And so this again is the area of b. So the area of b right, can be computed if we've got a curve C by integrating C around C counterclockwise, minus y dx, or either way, integrating x dy around C. So this is an application that's sometimes made of Green's theorem. Let's take a look at some specific examples where Green's theorem allows you to simplify a problem involving integration. Let's look at the integral around C of 4y minus sine x dx plus cosine y squared minus 6x dy, where C is the circle with radius 2 centered at the origin. Right. Then what? This is P dx plus Q dy, and Green's theorem says that this integral is equals to the double integral over the circle of radius 2 centered at the origin, partial of q with respect to x. That's going to be minus 6 minus the partial of p with respect to y, which is minus 4. Right? And we want to integrate this with respect to area, and so this is equals to minus 10 constant times the area of the circle of radius 2, centered at the origin, or the circle of radius 2, which is pi r squared, or pi times 4. So minus 40 pi is the answer to this integral. And clearly, if you tried to do this by parameterizing the circle, then you'd find that you'd have a much larger problem. So here's an example of where Green's theorem simplifies a problem. Let's take a look at another. Let's look at the integral of 4xy dx plus 3x squared dy. And let's let our curve now be this. We're going to follow y equals x squared around like so. And we're going to come back over here like this, around this simple curve like so, where this is the line y equals x plus 1. Right. So our curve goes around here like this and back. We want to find the integral around the curve here of this like so, 4xy dx plus 3x squared dy. Well, that's p dx plus q dy. So we want to take the partial of q with respect to x. That's going to be 6x minus the partial of p with respect to y. That's going to be 4x. We want to look at the double integral over this region. Well, that's the double integral over the region is going to be the integral from x squared to x plus 1 of this quantity with respect to y, and then the integral from minus 1 to 1, this goes from minus 1, oops, not to 1, to 2. Right? This point right here is the point minus 1, 1, and this point right here is 2. When is x plus 1 equal to x squared? Well, let's make this x plus 2 here, in which case this is going to be 2, the point 2, 4, to change the problem. And what's this going to be? Minus 1, when x is, this is going to be minus 1, 1. So let's make this y equals x plus 2. Simplify. We really don't want to do the most complicated problems. Just we want to go from minus 1 to 2 here, and then from x squared to x plus 1. And evaluate this integral. This is going to be what? 2x, and this is with respect to x now. This is going to be 2x, and I differentiate with respect to y, so it's going to be 2xy evaluated from y equals x squared to x plus 2. Right? And then the integral of this from minus 1 to 2 with respect to x. Right? It's clear that this problem has been made easier. We evaluate this from y equals x plus 2 to y equals x squared. Right? And we then evaluate the integral from minus 1 to 2 with respect to x. And Green's theorem has allowed us to compute the integral around this curve by doing the double integral here with respect to area. Consider subject matter which is known as flux here. If there's a curve in a vector valued field given by f, right, and this is a curve c, it's reasonable to ask if this curve represented the velocity of the fluid at any given time t, how much fluid would, and the velocity was this constant f at each point, how much fluid would pass through this curve c per unit time. Right? And the answer to that consists of taking f, right, dotting it with little n, where little n is the normals to the curve, so that if the fluid is flowing in this direction here, we take f and we dot it with little n, a normal, unit normal vector, c, right? This is going to give the component that is going through the curve, so to speak here. We would want to integrate that over the curve from, with respect to length. So that if this was the velocity here, we would take the velocity times a piece of length, and that would give you the amount of fluid flowing through here, the area of fluid here per unit time. Right? And so this right here is frequently written as phi, and it's called the flux. Now there's an interesting theorem involved here if C happens to be a simple closed curve. So if this is our C here, what we want to do is we want to integrate around C f dot n with respect to S. Well, now what is n? Well, a unit tangent vector here to the curve is given by, if C is given by r of t, right, and the unit tangent vector is given by v of t divided by the magnitude of v of t. Right? That's to say, it's x prime of t I plus y prime of tj divided by square root x prime of t squared plus y prime of t squared. That's a tangent vector. Now if we took a unit tangent vector and crossed that with k, so if this was a tangent vector here, we crossed that with k, where we imagine k is coming out from the board, what we're going to get is a unit normal vector, and the normal vector here that we're interested in is the one that is pointing outward from the curve C. Right? So t crossed with k is going to give us a normal vector, and the normal vector consequently, now this of course is at any time t, is going to be given by minus y prime of t I j crossed k t crossed with k. J, this is going to have I component. J cross is going to be y prime of ti minus x prime of tj over square root x prime squared plus y prime squared. All right. You can see that n of t is perpendicular to t of t here by simply looking at the dot product and seeing that it's 0. Here we get x prime y prime minus x prime y prime. So the dot product is 0, and this is a unit vector, and the direction is right because we've computed it by using t crossed with k. So this integral around the curve C of f dot n ds is going to be equals to the integral f of r of t dotted with y prime of ti minus x prime of tj over the square root x prime of t squared plus y prime of t squared. Now this is ds, so that's ds dt dt. Right? Well, this is ds dt. So this cancels with this, and this then is equals to f of r of t. If f is equals to pi plus qj, this is equals to p of x of t y of t times y prime of t. Right? That's the I part dotted with the I part here, minus q of x of t y of t dotted with x prime of t. So we want to integrate this from, if the parameterization was from a to b with respect to t. Right? That's to say this is equals to the integral of around c of p dy, that's how you compute p dy, p of x of ty of ty prime of t dt, minus q dx. this looks suspiciously like Green's theorem. Green's theorem says is that the integral of p dx plus q dy around C is equals to the double integral over the region B of partial of q with respect to x minus the partial of p with respect to y. The double integral is with respect to area. Right? Here we have got minus q taking the place of p. Right? So if we put minus q takes the place of p, so we put that in here for p, we get q, partial q with respect to y over here, and here we've got p dy taking the place of q. So if we put that over here for q, we get p with respect to x. So we find that this is the flux. It's p with respect to x plus q with respect to y integrated over the region B with respect to area. Well, this is the integral of the divergence of f. Partial p with respect to x plus q with respect to y is the divergence of f. We integrate it over B with respect to area, and it gives us the flux, the integral around C of f dot n ds. So this is a sort of a small version of a theorem which is called the divergence theorem. And it says that, okay, we can compute the flux here by integrating the divergence with respect to area over the region. There are two topics which will be just handled briefly here. And they generally are the concluding part of a calculus course. And the two topics that concluded require what are called surface integrals, and they suggest that there's a lot more that one can do here in the form of advanced calculus. And the idea of a surface integral is to integrate with respect to capital S a function f of x, y, and z. This is usually indicated as a double integral, and the idea is this. Got some sort of a surface here. Let's say u, and we've got a function f of x, y, and z, and we would like to find out how much of this, if this, for example, was in charge per unit area, how much of it was available on the surface u. If this was in weight per unit area, how much weight was on the surface u. And there are other uses of what are called surface integrals. We can really only deal here without much more elaborate theory with the simple case where this surface here is given by the graph of g of x and y equal to z. All right? So if this is g of x and y equal to z above a given region B here, right, then this integral over u is going to be obtainable by taking an element of surface area here, that's to say the square root of partial of g with respect to x squared plus the partial of g with respect to y squared plus 1, and integrating f of x, y, and z here, where now here z is g of x and y, right? We want to integrate this with respect to y and with respect to x over the region B. So in the event that the surface was a simple one here, it was just defined above a particular region in the plane, in the xy plane, the surface integral would be defined like this. Right? There are clearly two other situations which one can deal with. One is where the surface lies over some region in the xz plane, in which case, if this was y equals h of x and z, then the surface integral for a surface like this would be given by, well, let's say if this is v, the double integral over v of f of x, y, and z with respect to s would be given by the integral over d here, let's say, the double integral over d of f of x, y, and z, but now here y in this is equals to h of x and z, and now you integrate with respect to surface area, which is given by the square root partial h with respect to x squared plus the partial h with respect to y squared plus 1 with respect to z squared plus 1, and now this is dx dz and over the region D. Right? A third situation here, clearly, if the surface could be viewed as a surface here above a region in the YZ plane, you've got a similar situation here, and the surface integral here over W, let's say, of f of x, y, and z with respect to surface area can be determined in a similar fashion in which this was. So, without going into any more details than this, the surface integral can be evaluated in a fashion like so, provided the surface can be broken up into ones which are simple in this fashion right here. There are two final theorems that are generally given in a Calculus 3 class. These are the Divergence Theorem and Stokes Theorem. The Divergence Theorem says the following: that if you've got a surface U enclosing a volume V and a unit normal vector to U in a force field F, where U encloses the volume W, I should say here, then you can compute the so-called flux outside of this surface. That would be the integral of F dot M ds over the surface U by integrating the divergence of F over W with respect to volume. All right? Stokes' theorem, on the other hand, says that if you've got a surface here, not enclosing a volume, but a surface bounded by a curve, C, if the surface is U, and if a normal vector to the surface is N, and this exists in a force field f of x, y, and z, then you can compute the curl of F dotted with the normal with respect to surface area by integrating around C F dot T with respect to length. That's to say, by integrating F dot dr around C. Now, both these theorems are too complicated for us to really do any justice to, and they certainly suggest that a more advanced class in calculus is something that can be done.